That's just to let you know, we'll be uploading our feed to YouTube sometime later today. Our speaker today is Michelle Manus. Michelle is a professor out of the University of Hawaii. She's done research in number theory. And she has an extensive background working with K-12 educators and bridging the gap that's there. Today, she's going to be talking to us about falling back in love with math and about her journey back toward math through some chaos, I guess, right?
Yeah, so here, I'm going to go ahead and share my screen. Hopefully we did this in the run through and it worked.
And as you're getting set up, I see a lot of new faces here. We've been doing a thing called Featured Friends, where sort of a round table of people leave their mics on, so it sort of feels like a community. I monitor the chat, so I will amplify things into the conversation, but it's still totally appropriate to unmute and ask depending on what our session leader wants. So. Yeah, so the folks that I asked to be my featured friends were Bella, Jackie, and Matilde, who are all here. So if you guys want to unmute and like be my peanut gallery, that would be awesome. And great, so should I get started? Awesome. All right, so yeah, I'm Michelle Manus, and I will start, as I always must these past couple of years, with a disclaimer, especially for a talk that is going to get into some more personal things. And so I currently work at the National Science Foundation, and the views that I speak are my own. I most definitely do not speak for either of my institutions, either for NSF or for University of Hawaii. But I am grateful for the opportunity to work for both of them. All right, so this is going to be sort of a story that interweaves math and personal stories about me and my relationships with math. So it starts in childhood. And I am the youngest of 4 kids, and kind of by a lot. And in my family, we used to play blackjack all the time. We played blackjack for M&Ms, and you could only eat your winnings. And so by the time I was about 3, I could add to 21 in all kinds of ways. I was highly, highly motivated to learn at least basic arithmetic very young so that I could kind of keep up with my siblings. And also my brother was really into math. And so I kind of got super motivated. I invented what algebra might be when I was about 5 or 6 because he would come home with these like math problems that had letters all over them. So I just kind of invented what that might mean. So I decided like A stood for 1 and B stood for 2 and so on. And I made up math problems for myself. And I was really into science and into the idea of being a scientist, of figuring something out. So my idea of a scientist was it was somebody who figured something out that nobody ever knew before. And I thought that seemed pretty cool. So I was really into science, but I also wasn't like the kid who went to math camp or science camp. I was really a theater nerd. And so that's a picture of me at 5 years old playing the 5 of Hearts in Alice in Wonderland. And I did children's theater like from the time I could audition. Basically, I was like 3 or 4 until I was a teenager, and I did a lot of dance and a lot of other kind of performing arts. Although I never really kind of seriously thought of that as a career, but I definitely was not like the kid who, you know, sat at Erdish's knee when she was 10 or whatever, like Terry Tao did. And then the subliminal messages thing is just that my mom swears that she came into my bedroom at night when I was a kid and would just whisper, "You love math and science. You love math and science." So I don't know if that's true, but she swears that anything I've done is a credit to her. Okay. So in high school, I continued my fascination with science, and I kind of honed in on chemistry as the thing I was super into. And that was what I wanted to do. And math was fine. I liked math a lot. I was good at it, but it always seemed just like a tool that you learn to do other sciences up until I got to calculus, and calculus was the first time that I thought math was really interesting. So thinking about infinity and thinking about infinitesimals, that was the first time that I was like, huh, there's like something interesting to think about here. So I certainly hadn't switched over to considering being a mathematician. I don't think I even really knew there was such a thing as a mathematician yet. But I definitely thought math was sort of more interesting and worth more of my time. So I went to Berkeley for undergrad, and I entered as a chemistry major. And my calculus teacher at the end of the year pulled me aside and asked what I was taking next. And I said, well, I'm done. Like the calculus sequence is what you need for a chemistry major. And he said, well, keep taking math and come talk to me before you stop. And he also talked to me for a really long time about things I could do. He was actually like an applied mathematician, and he was like, I know you're into chemistry, but there's all these things you could work on. Let me talk to you about some like math research that has to do with chemistry. And if you take these classes, then you can come do a research project with me about this. And it was probably the first time I kind of understood that math was a science, and that this thing that I was really interested in science, about wanting to figure something out for the first time, something nobody ever knew before, that was a thing you could do in math. And so it was really eye-opening for me. And this idea of just how powerful it is to just tell someone to keep going and come talk to you before they stop is really, like, I try to do this with all my students now, because I think it's just having somebody give you those encouraging words really matters. And so I did keep going. I didn't end up in applied math. I started taking a lot of pure math classes, set theory and logic, and continued to get my mind blown by things about infinity, like so that Hilbert's Hotel was, super fun. And so that was where I was in college, but there was a little bit of a darker side to it as well. So I was a woman in a department that the year before I arrived, they had denied tenure to Jenny Harrison. So Jenny Harrison is on here. I have never met her, but she has had like a huge impact on my thinking about being a woman in math and on my career. In ways that she can't possibly know. But the tenor of the department was so colored by her tenure case. So she was denied tenure the year before I arrived. She was suing the department and the university for sex discrimination the entire time I was there. And the year after I graduated, she won and she was reinstated. And she's now a full professor with tenure at Berkeley. But the department was an ugly, ugly place. So not only did I have to deal with the usual kind of harassment and bullying and everything that most women in most math classes have to deal with, and just gross stuff. I won't go into it, but it was not pleasant. But on top of all that, there was just this overlay of the feeling that I was being told really explicitly that I didn't belong there in a very powerful way. And in fact, my undergraduate advisor, when he found out I wasn't applying to graduate school, got really upset and had his daughter like email me and tell me about how great graduate school was. And so at our next meeting, I said, well, why would I go to graduate school just so that you could deny me a job in 6 years? And he kind of sat there open-mouthed and didn't know what to say. And so, so like there were positives and negatives. I really liked the math, but by the time I graduated, I was really done with math in a lot of ways. I was really angry and hurt, and I felt like I didn't belong. And at the same time that I was doing a BA in math, 2 blocks away, there was a community college that was giving classes in American Sign Language, and I got a 2-year degree. So basically 2 days later, after getting my bachelor's in math, I got an associate's degree in American Sign Language. And I had become kind of the de facto babysitter of every deaf kid in the city of Berkeley, because I was a grown-up with transportation who knew sign language. And so, so I ended up going to graduate school in deaf education. I went and got a master's degree in deaf education. So, oh, and that picture is Cindy McDougall. She was my first ASL teacher and became a good friend and a mentor to me. And that's a snapshot from videos that people use to teach sign language. And the picture up on the left is a picture of the school. It's not me, but it's the school where I used to teach. It's called the Learning Center for Deaf Children. So I got a master's degree in deaf education at Boston University. And so it was deaf education with a specialty in mathematics. And I went and taught at this school called the Learning Center for Deaf Children, just outside of Boston. I later on went and taught at a public charter school called City on a Hill, and that was just teaching, hearing kids, just 11th and 12th grade math. And I also worked at this really amazing place called Education Development Center. I worked doing education research and curriculum development. And I spent, I guess, not quite 10 years there. And I think Al is on. I told him if he came on, he was going to see a picture of himself. So this is Al Coco, who I think is in here somewhere. But he
just waved at you, Michelle.
Oh, I can't see him, but hi, Al. So Al was started off as my boss and became my colleague at EDC, and was so instrumental in my continued mathematical growth and then bringing me back to math. So all these things I did while I was working in K-12 education, my favorite thing was like sitting and learning math. So at some point, you know, Al was like, let's do some stuff on cryptography, and handed me some books. And I went and sat in my office for a couple of weeks and learned a bunch of cryptography in order to write like a chapter for a high school textbook. And when I was working in schools, I was the like teacher who brought math problems to the faculty meetings. So instead of talking about problem students, we would talk about like the problem of the week from my book that I thought was really interesting. And every year, Al would write in my annual report, the last sentence would be, Michelle needs to go back to graduate school and get her PhD. And so eventually, I will say inertia is strong when you work a really fun, supportive place. It can be hard to step away from that, but I eventually did. So I applied to graduate school and went back. But that story is going to come in a little bit, because I'm going to take a little detour. So one of the great things about EDC is that they had a tuition reimbursement program. So you could take classes and learn stuff as long as you could say that it was somehow related to your job. So I would take math classes at Boston University, and Al just signed off on any math class I wanted to take. So I went and took a dynamical systems class from this guy, Bob Devaney, at BU. And so now I'm going to sort of move away from the personal story for a little bit and start telling you about my favorite theorem in math. This is, so when Evelyn was here a couple weeks ago and she said I had done one of the short snippets, this was the theorem I talked about. So I'm going to do a little bit of introduction. So we'll start with an iterated dynamical system. So you're going to start with a set, just any set, and a self map. So a function on the set. And I'm going to use this exponent notation to mean iteration. So the infold composition with itself. And kind of the fundamental question that you ask in dynamics is to classify points of the set according to their orbits. Okay, so what does that mean? So let's look at an example. I'm going to take a function of complex numbers, so from C to C, and it's just very simple, z squared minus 1. So can my featured friends tell me what happened when I start with 1? Where does 1 go?
0.
1 goes to 0, and then 0 goes to?
-1.
-1, and then -1 goes to?
Back to 0.
Back to 0. Okay, so there's, right, that's classifying points according to their orbits. This is one possible orbit. So I'll say that 1 is what we call pre-periodic. And 0 and -1 are periodic of period 2, right? So they enter a loop. So the golden ratio, so this is supposed to be the golden ratio. I don't expect you guys to actually calculate this, but I'm just going to point out that if I wanted to find fixed points of this function, I would want to solve z squared minus 1 equals z. In other words, I would want to find roots of z squared minus z minus 1. And that's exactly the equation that defines the golden ratio. So this guy is actually a fixed point. He maps back to himself when you plug him in. And also his Galois conjugate does the same thing, right? Both roots of that polynomial are fixed. Okay, so now I'm going to start with a point that's really, really close to that Galois conjugate. So all I did was take the decimal expansion and truncate it, right? So I started with 0.618. So if you picture the real line, right, here's 0, here's minus 1, here's that number I'm starting with. And I started with something like just a little bit smaller, just a teensy bit. And oh yeah, well, okay. So, and what happens? So if you iterate, if you kind of focus on the left column, it looks like it's kind of fixed, right? Like it's not getting very far away. But if you go out for a little while, so I jumped about 40 iterates to get over to the right column. What do you see happening there? Anybody have a, what do you see there?
So the right column is chaotic.
Well, I mean, it's, yeah, so it no longer looks like it's fixed, but in fact, if I look at, right, this is kind of close to minus 1, and this is kind of close to 0.
I go between one and the other.
Yeah, so it's actually, so like I kind of jump around a little bit, but eventually I kind of am getting closer and closer to that 2 cycle, that 0, minus 1, 2 cycle. I'm never going to get there, but I am getting closer and closer to it with each iterate. Okay, so now I'm going to start with another point that's very, very close to, oh, no, sorry, this was a typo, to the conjugate, to that minus 0.618. So now I'm thinking, right, remember it was a function on the complex line. So instead of taking that number, I'm just going to take that number plus a little tiny imaginary part, right? So I did 1 times 10 to the minus 6th I. So this is my seed value right here. This little tiny imaginary part added on. And again, if I look at just the right column, or just the left column, sorry, just the first few iterates, it stays pretty close to where I started. It doesn't do very much. But again, I jump out about 40 iterates to get over to the right column. And now what do you see? What's going on there?
Numbers are getting larger.
Yeah, they're getting giant, right? Like it goes, you know, it's about, you know, minus 20 plus 33i, and then minus 740, minus like 1300i, and then just bigger and bigger from there on out. So, so just nudging it a tiny bit off this fixed point created very dramatically different behavior depending on which way I nudged it. All right. So overall, the idea is in complex dynamics, you kind of capture these different kinds of orbit structures in really pretty pictures. So here's a filled Julia set for this function, z squared minus 1. All those black points, those are the points where the orbit does not go to infinity. So it includes, for example, right, there's that fixed point right there. Here's our 2 cycle right here. But all these other points, they also have what's called a bounded orbit, right? It never gets too big, but the points in blue, those are the orbits that go off to infinity. So I can draw these lovely pictures, and what these pictures are really doing, right? That fundamental goal of dynamics, classifying points of the complex plane according to their orbits, according to what happens under this function. Okay, so let me pause and see if anybody has questions before I go on to the next little section. Good, okay. So let's move on then. All right, so I kind of hinted at this, but the fundamental game of finding periodic points for a function it comes down to finding roots of polynomials. So if I want to find fixed points, like I was finding that the golden ratio was a fixed point of that x squared minus 1 polynomial, I find a root of f of z minus z. And if I want to find a point of period n, I find a root of the polynomial that is like the nth iterate minus z. And so you might say, well, I learned the fundamental theorem of algebra, and I know that the complex numbers contain roots of every polynomial you might care about. So the polynomial, every polynomial that I could ever write down will have points of every possible period. But it turns out that that's not true. So let me give you an example. Here's a really simple polynomial, right? Z squared minus 3/4. If I want to find fixed points, whoops, well, I'll just leave them both there. If I want to find fixed points, I want to find roots of f of z minus z, and I just factored it for you there. So my fixed points are what? 3/2 and minus 1/2. And you can plug those in and check that they really are fixed. If I want to find points of period 2, I want to take the polynomial z squared minus 3/4, square it and subtract 3/4, and then do that whole mess minus z and find roots. And it turns out, if you're bored, go ahead and do the algebra. But this is what you get. You get that factored form right there. And so what do you notice?
They're all actually fixed points.
Yeah, so it's the exact same set of roots, right? I have some multiplicity, but the fixed points, the roots of the first polynomial and the roots of the second polynomial are identical. So I don't have any points of period 2. Even though the polynomial has roots over the complex numbers, I don't actually have like a genuine point of period 2. It's like fixed points masquerading as points of period 2. But in fact, that's the only thing that can happen over the complex. So I gave you the one counterexample. So here's a theorem by Ian Baker. So if I have a rational function defined over a field of characteristic 0, then over its algebraic closure, so just think over C, right? If I'm missing any periodic points, then I can exactly classify the period that's missing and the degree that the function could be. And moreover, if f is a polynomial, the only thing that's possible is a quadratic function that's missing a point of period 2. So I gave you, in fact, the only example that exists for polynomials where over the complex, it doesn't have periodic points. Okay, but what if I don't care about the complex numbers? What if I care about the real numbers or the rational numbers or some other field, right? The x squared minus 1 is perfectly happily defined over the reals. So I could ask the same question there. And it turns out there's this remarkable theorem. So I'm going to tell you now about Sharkovski's theorem. We have to start by defining an ordering on the natural numbers. And I'm going to have to ask you guys to remember this ordering as we go through the theorem. But it's a pretty easy one to remember. So 3 is the biggest natural number. 3 is bigger than everybody. And all the odd numbers are biggest to smallest in what we usually consider increasing order, right? So 3 is bigger than 5, 5 is bigger than 7, 7 is bigger than 9, 9 is bigger than 11, so on and so on, okay? Every odd number is bigger than every number with a single factor of 2. And the biggest even number is 6, right? So 6 is bigger than 10, 10 is bigger than 14, 14 is bigger than 18, and so on. Things with a single factor of 2 are all bigger than anything with a factor of 4, right? So 18 is bigger than 12, but 12 is bigger than 20, which is bigger than 28, and so on. And hopefully you're getting the pattern, right? So increasing powers of 2 make a number smaller. And if I don't have any odd factors at all, I'm smallest of all. And then 1 is the smallest natural number. So the powers of 2 actually decrease, right? 4 is bigger than 2 is bigger than 1. Okay, so this is my ordering of the natural numbers. Can we remember it as we move on? Okay, All right.
Actually,
So,
I have a question.
yes.
So I don't understand. Like, say 4 is smaller than 2 to the 5th multiplied by 3. Okay. So any power of 2 is smaller than anything that has an odd number.
Yeah, an odd factor. Yeah,
odd factor. Yeah. Okay. Okay, thank you.
Yep. Any power of 2 is smaller than anything with an odd factor. And then the powers of 2 are in kind of what we would consider the usual decreasing order. Okay. So here's the theorem. Suppose I have a continuous function on the real line, and I have a real valued point of, so when I say primitive period n, I just mean least period. Like I don't have a fixed point that, you know, is appearing as a period 2 point. It's really genuinely period n. And that n is bigger than k in the Sharkovsky ordering, then f also has a real valued point of period k. So in particular, remember 3 was my biggest natural number. If I have a point of period 3, I have a point of every possible period. So this is why the theorem is sometimes called period 3 implies chaos, right? So if I have a point of period 3, I have every possible period. Okay, any questions on the statement of the theorem, what it's claiming? All right, so the idea of the proof, I'm gonna just give you a couple of observations and then we're just gonna hit these two observations over and over again. So the first one says, suppose I've got a closed interval on the real line and that under this, you know, mysterious continuous function f, the image of that closed interval contains the interval itself. Then I have a fixed point in that interval. So my picture is trying to show, right, that I have, so the blue curve is my function f, the yellow line is my function y equals x, and you can see there's my fixed point right there where those two things intersect. But in fact, like we don't have to rely on pictures. This is just the intermediate value theorem. So if I apply the intermediate value theorem to that continuous function f of x, well, it takes on every value, right? F has to take on every value in f of I because it's continuous. So in particular, at some point it takes on the value a, but since a is my leftmost endpoint, right? A is over here. The place where it takes on that value has to be bigger or equal to a. And similarly, someplace it takes on the value b, right? But b is my rightmost endpoint. So the place where it takes on that value has to be less or equal to b. But what does that say? That says that the function, and now if I think about the function f of x minus x, which is also continuous, it changes sign somewhere, right? It's negative one place and it's positive another place. And that means it's 0 someplace. And where it's 0, that's where I have a fixed point, right? So just the intermediate value theorem tells me this works. Okay. Observation number 2 is maybe even more straightforward. Suppose that f of I, so the image of my interval I under this continuous function contains some closed interval j. So that's what I've tried to show, right? This vertical strip is all the y values that I get. That's f of I right there. And it's bigger than that interval j. That says I can kind of shrink my interval I down to where I exactly land on j, right? There may be more than one subinterval that works, but there's always at least some subinterval that works, that gets me exactly j as my image. Okay, so that's all I need to prove this wild theorem, basically, is those two observations. So let me pause and see, is everybody believing observation 1 and 2? Does anybody think I'm lying to you?
There was an observation that the original theorem didn't require polynomial, it only required continuity.
Yes, isn't that, so this is, there's a slide about what I love so much about this theorem, and the simplicity of the hypothesis is one of the things that only requires continuity. It's wild, yeah. Okay, so I'm gonna do just a couple of the cases. So first I'm gonna convince you that if I have a point of any period at all, I definitely have a fixed point, right? So suppose I have, so the cycle consists of these points x1, x2 up to xk. And I've listed them in increasing order, just like they're real valued points, right? And they're in increasing order. This may not be the order the cycle comes in, right? The cycle might go like x1 to x5 to x2, right? The cycle could jump all over the place. I've just listed them in sort of increasing order of absolute value. Or not even, just like literal increasing order, not just absolute value. Okay, but the point is the argument is almost the same as that first observation I gave. So f of x1 maps to some other point in the cycle, and that point is bigger, right? Because x1 was my smallest point. And similarly, f of xk maps to some other point in the cycle, and that point is smaller. And so using exactly the same argument, right, I look at that function f of x minus x on that interval, and it switches sign, right? It's negative at x1 and it's positive at xk. And so somewhere in between, it's got to be 0. And so I've got a fixed point in there somewhere. Everybody convinced? All right. All right, second case, I'm going to convince you that if I have a point of period 4, I've definitely got a point of period 2. So same deal, right? This is, my cycle is x1, x2, x3, x4. That doesn't mean x1 maps to x2 and x2 maps to x3. It's just listed in increasing order. And I'm going to choose an A that splits the segment. So x1, x2 on one side, x3, x4 on the other side, right? So that's my point. This is my point A right there. And so there's a couple of possibilities. I'm just going to work through one of them. The other one works the same way. It's just different bookkeeping, right? So either you could either have something like x1 maps to x2. Well, then x2 can't map to x1, right? Because that would make it a 2 cycle. So x2 would have to either map to x3 or x4, right? So either one of them maps over to the other side, or they both do, right? It could be the case that x1 maps to x3, x2 maps to x4, and then these guys both map back in some way to make a cycle. Those are kind of the two things that can happen. I'm going to only consider this case, the one where they both map over A. The other case is very similar. Okay. So I'm going to assume, and again, I've sort of made some labeling choices. I could easily say that this is f of x2 and this is f of x1 if I wanted to. It's just a labeling choice. But all I've done is said x1 maps to either x3 or 4. x2 maps to the other one, right? But then that says that that interval contains, under the image of that interval under f, contains that whole interval x3 to x4, right? And similarly, x3 has to map to either x1 or x2, right? So x3, I chose x2, but it doesn't matter. It could be either one of them. x4 has to map to the other one. So this whole interval, x3 to x4, has to cover that interval x1 to x2, right? And now is when I use my observations. Okay, so since this interval I1 has to cover the interval I2, I just choose some sub-interval that hits it completely, right? I choose this A1 so that it actually works exactly right. And then, since this interval I2 covers I1, there's some interval, well, so then, yeah. So then when I do it 2 times, right? I take A1, it lands on I2, and I map back, it more than covers I1, right? It at least covers it. So if I take the kind of double image of A1, it has to cover I1. But that says that using observation 1, right, I have this continuous function that maps A1 back over itself. And so there's got to be a fixed point in there somewhere. Okay, so now the tricky thing is, how do I know I really have a point of period 2 and not a fixed point? Well, the answer is, whatever C is, it starts over here, it comes over here, and then it comes back again, right? So it can't be a fixed point because it hops back and forth between the two intervals. Okay. So it's really just bookkeeping, right? It's just keeping track of these intervals in bookkeeping. Okay, so the last case is that I'm going to do, right? There's a bunch more cases, but the last case is period 3 implies every period. And again, there's two possibilities, right? If I label them, A goes to B goes to A goes to B goes to C and back to A, kind of, you know, by rearranging things, I can make sure that A is my smallest, and then I just don't know, is B smaller than C or is C smaller than B? I don't know. But again, they're nearly identical. So I'm gonna assume this case, that it goes, you know, small, then the next biggest, then the biggest, and back again. But the other case is really similar. Okay, so now I've got I0 is gonna be this first interval between A and B. I1 is gonna be the second interval. And by what I've set up, right? I0, the image of it has to cover all of I1, and I1, the image of it has to cover the whole interval, right? Because B maps to C and C maps to A, so it kind of wraps around. So when Evelyn asked me, when I did my favorite theorem, like what this paired with, I said taffy, because it's like you're pulling taffy, because this interval like stretches and wraps around itself and covers itself completely. Okay, any questions on the setup? All right, so the whole game is that I'm going to use this observation 2, this fact that I can just shrink the interval down so that it covers completely exactly, right? So that the image is exactly what I want. And I'm just going to use it n times, right? If I start with a point of period at 3 and I want to get a point of period n, I'm just going to do that observation n different times and it's going to work. And I'll just point out, so that works for n bigger than 3. So in particular, it works for 4, and I already proved that 4 gives me 2, and anything gives me a fixed point. So then I'll be done. I'll have that period 3 implies everything. Because period 3 definitely gives me 3. It gives me everything bigger than 3, here bigger in the like normal ordering, right? And then then that gives me 4, 2, and 1. Okay. So by everything I've set up, okay. So since f of I1 covers I1, I choose a subinterval that covers it exactly. And then I do that again. Since f of A1 covers I1, which contains A1, right? I choose a subinterval that covers A1 exactly. And then I do it again. And I do it n-2 times, right? So I just keep choosing these subintervals so that f of an-2, the image is exactly f of an-1. F of an, sorry, the image is exactly f of an-3. F of an-3, the image is exactly f of an-4, etc., all the way up until I get the image is exactly I1. Okay. And then I use the other thing I know, which is that I0, this interval over here, exactly covers, well, more than covers I1, so I can choose a subinterval that exactly covers any piece of it I care about. So I choose this little subinterval an-1 so that it covers an-2, which covers an-3, all the way up, which covers I1, right? And then one more time, little an over here, right? Again, I1 covers the whole interval. So in particular, it covers I0. So in particular, it covers an-1. So this little subinterval right here covers an-1, covers an-2, an-3, all the way up, exactly covers I1. Okay. So by this whole mess, I've set it up so that if I apply f n times to this little tiny interval, right? It goes 1, 2, 3, 4, 5, all the way up here, and it covers itself again after n applications. But then there must be a fixed point in there, right? Because the nth iterate covers itself, and so there's a fixed point. And how do I know it's genuinely a fixed point and not like something disguised or like a point of period n? How do I know it's generally a point of period n and not something of smaller period disguised as a point of period n. And it's because it only hops over to this interval one time, right? So it starts here, it hops over here, and then it spends the whole rest of its life over here. So it can't possibly be period less than n, and it can't be period more than n. So that is the end. Okay. So I'm just going to do my little like why I love this theorem, and then I'll pause for a minute and see if you guys want to ask me anything. So why do I love this theorem? As somebody already pointed out, simple hypothesis, continuous function. That's all you need. Powerful conclusion, right? Period 3 implies chaos, but even more than that, like all this stuff about if you know a particular period, you know every period less than that. The proof is really elementary. It's really just bookkeeping and the intermediate value theorem. You can do this in a calculus class if they had the patience for it. But it also feels like magic, because where in the world did that ordering come from? Like, where did that come from, right? So it feels like there's this little piece, there's this like little magical piece that I can reproduce everything, but I can't quite figure out how they came up with it, right? And that's the part that is really sort of exciting and kind of grabs me. Okay, so let me pause before I go on and see if anybody has questions.
So the big one from the chat has been the intermediate value theorem essentially encodes the big assumptions about the reals and the continuum. So there's been this question about, does this theorem generalize to other continua? And it looks like somebody found that Helga Schirmer proved that any linear continuum is a Sharkovsky space, a topological space where this theorem holds.
That's awesome.
Yeah. Wow.
That's very cool. Yeah, that's exactly right. Yeah, because it's not really using anything else, right? Anything where the intermediate value theorem, some version of the intermediate value theorem holds, this is going to work. Okay. Any other questions? Okay. So
Joshua had one.
Oh yeah.
Can you compare and contrast the theorem about rational functions skipping periods with this theorem?
The one about the complexes?
I think so.
Yeah, so the complex, that proof is really different, right? So that proof, you're really using, I mean, you kind of use a Taylor expansion of the rational function, of like f of z minus z as a rational function. You kind of use a Taylor expansion of it, and you can understand if something, so right, there really are roots of those polynomials over C. It's not that there aren't roots. There are all the roots you want. It's just that what can happen is exactly what you saw. A fixed point can show up as a period 2 point, but with multiplicity. A period 2 point can show up as a period 4 point, but with multiplicity. And when that happens, it has a very particular meaning about what's going on in the Taylor expansion, especially just the first coefficient, the linear coefficient of that Taylor expansion. And so you kind of unpack what's going on there. So the proof is like completely different. It's a completely kind of like, yeah, the proof is all about understanding what it really means is that kind of cycles are collapsing, right? If you imagine like a family of functions that are getting closer to yours, you've got like a 4 cycle collapsing into a 2 cycle, and what that tells you about the Taylor expansion of the polynomial, and then just understanding when that's actually possible to happen.
So the difference between the real numbers and the complex
yeah.
Completely different behavior.
It's completely different, yeah. And I'll say, I guess I should say that there is a converse to this as well. So if you picture, I'm not going to try to scroll back, but if you picture the Sharkovsky ordering in your head, if I tell you, I can give you examples, I can build examples of continuous functions that are missing like points of every odd period except one, right? If you pick any cutoff in the Sharkovsky ordering, I can find you a function that has like that period and everything after it, but nothing before it. So there is a converse to this theorem as well. So you can miss like infinitely many periods over the reals. You can just construct them very easily. So
We have another question that just popped up. So you've used the word chaos.
Yeah.
Can you explain what that means in this context?
Yeah. Well, so, I mean, I can try. Okay, so the usual definition of chaos has 3 pieces. So you need to have sensitive dependence on initial conditions. So that's that first thing I showed you where if I nudge a point a little bit, the behavior changes. So I took a fixed point and I nudged it one direction and it got sucked into a 2 cycle, and I nudged it another direction and it just got gigantic, right? That's sensitive dependence on initial conditions. You have to have what's called a transitive orbit. So you have to have a single point whose orbit comes as close as you like to every other point in the space. And then you have to have dense periodic points. And so the period 3 implies chaos is sort of a way, it's kind of getting at that density of periodic points. If I have points of every possible period, that's how I get dense periodic points. So it's not quite enough to get what most people call a chaotic dynamical system, but it's sort of a shorthand for what this is encoding about the periodic behavior. Anything else?
We do have a couple more, but one of them was, how does this connect to falling back in love with math, which I think is maybe where you were
yeah,
going.
That's where I'm headed.
So
yeah.
We'll save the rest for the end.
Okay, let's do that. Awesome. Yeah, so after I took this class, shortly afterwards, I ran a workshop with Al for a bunch of math teachers, and these 2 guys, so Bob Devaney, who taught my dynamical systems class, and Glenn Stevens, who is a number theorist and was the leader of this Promise program that I was involved in. They were both kind of guest speakers. And over lunch, they were just chatting about math. So Bob does dynamics and Glenn does number theory. And Bob was asking Glenn all these questions and Glenn kept saying, nobody knows. Why do you want to know that? And I had been sort of, Al had been every year telling me I had to go back and get my PhD. And so I kind of said, hey, well, does anybody do this? Does anybody work at the intersection of number theory and dynamical systems, because I've kind of liked both of those things. And they said, oh yeah, there's this dude at Brown named Joe Silverman. Like, he's kind of the guy who does this. And so I kind of tucked that away in the back of my mind. But like so I guess I will say, like, doing Bob's class, it was a graduate level math class. I hadn't really been certain that I could do graduate level math, but that was a graduate level math class that I loved and excelled at. And I was, and I was coming to this realization that of all my jobs I was doing, my favorite part was always the doing math part of it. Like, all my jobs were mathematical in nature, and the sitting and doing math was always my favorite part of it. So I kind of finally decided to go back. And so I sent Joe an email. We were at a conference together recently, and he pulled up the first email I had ever sent him in order to, like, completely embarrass me in front of a lot of people. But yeah, I sent Joe like a total cold email and said, I heard you do this stuff and I'm really interested, and can I come talk to you? And so I did. I went back to Brown, and it turned out that a lot of what I ended up working on when I was working with Joe comes back to this question of, what if I change the field where the periodic points live, right? So I started with the complex, and then Sharkovski's theorem was about the reals, but there's lots of other fields out there. And in particular, if you're living at the intersection of number theory and dynamics, right, you might very naturally ask about the rational numbers or number fields, right, finite extensions of them. So it turns out that, so again, periodic points. So this stuff on the left about number fields, if you're not a number theorist, just think rational numbers. There is no harm in just thinking rational numbers throughout. But I'm going to take a polynomial with rational coefficients, and I'm going to ask questions about rational pre-periodic points, right? So we talked about pre-periodic points, like that 1 maps to 0, maps to -1. Periodic points are a subset of those. And it turns out, so way back in 1950, Northcott proved this theorem that said, so again, no harm in just thinking the rationals. If I take a polynomial with rational coefficients, I can have only finitely many rational pre-periodic points total. Like, I can never even get infinitely many, much less anything like this period 3 implies chaos theorem. And the idea of the proof comes down to what's called heights. So I'm just going to really quickly give you like the briefest overview of what this looks like. So if I take a rational number, I'm going to define its height to be the maximum of the absolute value of the numerator and the denominator. And I'll just say, for people who care about number fields, this idea extends really naturally, but it's just complicated to write down. Okay, so I'm going to ask my friends to help me write down all the rational numbers that have height less than 4. Can anyone tell me a rational number with height less than 4?
1/2.
1/2. And in fact, since it's absolute values, I'm going to go ahead and smack a plus minus on there. Anybody tell me another one?
1, 2, 3.
1, 2, and 3. And also, I can take negatives of any of those. What else?
2/3.
2/3. And I can take negatives of that. I think I'm still missing some.
1/3.
Yeah. And then I think I'm just missing some reciprocals, right? I can take 3/2. Is that it? Am I done?
0.
And 0. Thank you. Yep. All right. So yeah, it's a finite set. And I can just sort of enumerate them, right? If it's pretty easy to like write a program that'll do this. If I give you a height bound, you can write down all the rational numbers up to that height bound. And it's a true fact. And you can kind of, I mean, this kind of makes sense, right? If I have a polynomial and I plug in a rational number, say it's a degree D polynomial, kind of that lead term is going to dominate. So the height of the output is going to be pretty close to the height of the number to the dth power, right? The other terms are not going to matter so much. And it turns out that you can define a canonical height relative to the function where that's exactly true and where it's still the case that points of bounded height are finite, right? So it's not exactly, you can't write them down in quite as nice a way as we just did, but it's sort of a modulated height tuned to the action of the polynomial so that it exactly has the effect of raising things to the dth power. Okay, so I want to convince you that Northcott's theorem is true. So take a rational number that's going to be pre-periodic. So what does that mean? It means that two iterates coincide, right? I iterate for a little while and at some point I come back to where I was before. All right, now I'm just going to take the canonical height of both sides of that equation. And then I'm going to use the fact that canonical heights satisfy this, you know, it's raised to the dth power, except right, the degree of the mth iterate is not d, it's d to the m. The degree of the nth iterate is not d, it's d to the n. Okay, and remember how I defined height? It's like an absolute value of an integer. So what I have is like a positive number, positive real number raised to some power is equal to that same positive real number raised to some different power, where there's only one way that can possibly happen, right? Is if that positive real number is 1, right? That's the only number where when I raise it to 2 different powers, I get the same answer. And so then I have a set of bounded height, and so that set has to be a finite set. So notice this doesn't give me any way to find the points, right? It just tells me there's finitely many of them. But this is dramatically different behavior from either the reals or the rational or the complex. All right, so I'm just gonna say like 2 more words just really quickly. This is a big open problem that says, all right, so for any given function, I know there's only finitely many, is there some like uniformity? So for every, so the conjecture is for quadratic functions, there's some fixed number that is the maximum for every quadratic function. Right? It could be the case that every function has a finite number, but that finite number could be arbitrarily large, right? If you make the coefficients big, maybe you could get 300 periodic points or 1,000,000 of them or whatever without changing the degree. But there's a conjecture that says that doesn't happen, that in fact, like if I know my function is quadratic, you know, there's at most, in fact, the specific guess is there's at most 9 if my function is quadratic. But we don't know. We can't prove anything even towards this. The closest we can get are things like these two theorems. So one is my mathematical brother, Rob Benedetto, who can prove that there's kind of a function depending on the number of primes of bad reduction, which I won't, like, just think if I have denominators or a lead coefficient, any primes dividing denominators or a lead coefficient are going to be bad. And if I count up how many of those there are, sort of a function of that number will bound it. But that's not bounded, right? That could still be arbitrarily big because I can make the coefficients huge. And Nicole Looper has this very cool theorem that says the ABC conjecture implies it for things that look like z to the d plus c, but not, even then, that's not for all functions. Okay, so I will say just another quick word about my journey. So after my PhD, I did a very quick postdoc at USC, and then I went to the University of Hawaii, where I've been ever since. And after 10 years at University of Hawaii, NSF came calling and asked if I wanted to be a program officer. And since I had never done any job for 10 years, it seemed like a good time to go try another thing. So I've been at NSF for 2 years. I'm happy to talk to you about being at NSF if you're curious about that. And I mean, so the current plan right now is that I will go back to Hawaii next year, but I clearly have some kind of like ADD relevant to my careers, and I jump around a lot, so kind of who knows, but that's where I'm at. So let me see, we can come back to any of the questions, or if people have other questions, I'm happy to chat for however long.
First, let's thank Michelle.
Thank you.
Well, featured friends, do you want to go first? Do you have any questions?
So question.
Yeah, Ms. Hilde.
Yeah, so the 9 that impugns conjecture, is it 3 square or is it something?
No, okay, so yeah, Punen's conjecture, no, it's actually like he has examples with 9 and no examples with more. And so really what okay, so the theorem is really the following. If there does not exist a quadratic a quadratic polynomial with rational coefficients that has a rational point of period bigger than 3, then the total number of rational pre-periodic points can be no more than 9. So he's completely classified, right? Everything that has fixed points, 2 cycles and 3 cycles, and like has done every possible case to figure out what can happen. We can prove that there is no quadratic function that has no quadratic polynomial that has a rational point of period 4. We can prove there's no quadratic function that has a rational point of period 5. We can kind of, subject to a pretty powerful hypothesis, prove it for period 6, but we have no idea. Like maybe there's some weird quadratic function that has a rational point of period 22, and we just haven't stumbled across it. We don't know. And the techniques that we're using are just not gonna, like they've kind of tapped out. We don't really have much hope of pushing them. We really need a new idea. But yeah, no, it literally comes from like, there's a function with 9, here it is. And then there's not one with any more. So that's where, yeah.
Benjamin had a question a while back about the Sharkovsky theorem.
Yeah.
Are there variations of this theorem, maybe not in R or with some alternative to continuous, where instead of powers of 2 making stuff small, the initial ordering involves some other prime P that makes stuff small? And then there was a later comment about this feeling very 2-adic.
Yeah, so in fact, a very natural thing to do when one is a number theorist, Jackie should be smiling right now, is if you have a theorem over the reals, you should say, I wonder if there's a p-adic version of this theorem. And in fact, I have spent an afternoon, I don't know, maybe Jackie and I should talk about this at some point, because she is, p-adic dynamics is the world she lives in. It's really different in p-adic land in a lot of ways. Like periodic points behave, like everything is just really different there dynamically. And I convinced myself at some point that no version of Sharkovsky's theorem would hold for functions with good reduction, I think. but if you allowed for bad reduction, you might be able to make it work. Yeah, it's not at all, it's definitely not straightforward. I will say it is a very natural question to ask. That is a number theoretic question at its core. Like when you see a theorem over R, to say like what happens in QP. But I have not thought about it seriously enough to know if there's something there. But I'm definitely interested, Jackie, if you want to put this on. We're meeting tomorrow. Maybe
Yeah,
we
let's
can talk
chat.
about this.
Continuity will be a huge issue there. But
Yeah, exactly. Yeah, I mean, I doodled a bit, but I didn't get very far.
Well, we also had a comment way before somebody was excited about your book, and so I'd be interested in hearing about that. But we're at our hour,
Okay.
So let's clap one more time so we can stop our recording.
Thank you.
Thanks, Michelle. This is great.
And then if